with. Right. It becomes a linearized model. And for this linear now, this is autonomous system. So for this linear autonomous equation, equilibrium states are given by, suppose for this system, equilibrium state is given by suppose Xc. Right. Means Xc is satisfying this equation. Yes. So Ax E will be 0. It is going to satisfy. So Xe will be 0. If it is there, then Xe is equal to 0 will be the only solution then. Will be the only solution. If it is there, it becomes origin. So origin can be a equilibrium point. Origin can be equilibrium, provided delta A is not 0. Provided delta A, determinant A is not 0. Right? So when Xa is equal to 0, that is equilibrium point we get. When Xa is equal to 0, it becomes a origin. So origin can be a equilibrium point where the system is remain undisturbed. Well, system becomes undisturbed or it becomes stable. So in general, if Xa is a singular point, Xa is a singular point, it is convenient to shift the system to the origin. Shift, or we can shift that Xa towards coordinates of origin towards origin. It is convenient to shift the origin of coordinates X. Means you can make Xa as a origin. You can shift the coordinates. Now to achieve that, what is to be done? We have to achieve it. Achieve that, we define new phase variable as X tilde. So what is that? X minus X. That will be a new phase variable we can have. Tilde now. So if it is tilde, so what is that X tilde? X minus X. The system of equation B. What is B here? This is the system. Autonomous system. X dot is equal to f of x. Okay. So what is it? The system of equation. System of equation B in terms of new phase variable. Variable become as x tilde dot is equal to f of x tilde. Okay. So this will be get represented. Now x tilde is a new phase variable we have created, because we have to understand, we have to apply all the concept about stability towards that x tilde. Now stability, if we have, there are two notions for the stability, where the system can be a free system without input, and with input it becomes a force system. Now we have studied in the second year also. In the second year only we have studied free response and force response, isn't it? So stability is defined for the two notions. One, stability for the free system, stability for the force system. Now if it is a free system, free means what? Hmm? Anyone? Free means what? And force means what? Free means a system with zero input. A system with zero input. Initially maybe it may be, if the capacitor is there, if the inductor is there, it may be charged and it may be magnetized. But the input is taken out at t is equal to 0. There is no input. It becomes a free system. And when input is applied, source is applied at t is equal to 0, it becomes a force system. Okay. So it is a free system. A system is stable. Now for free system, what is the definition? System is stable. System is stable with zero input. With zero input and arbitrary initial conditions. Means it is loaded with the initial conditions. If resulting trajectory tends towards our equilibrium point, tends towards equilibrium point, our singular point, then it becomes a stable. So here it is written, system is stable with zero input and arbitrary initial condition. If resulting trajectory tends towards equilibrium point, it becomes a stable. So when the trajectory is important for the trajectory is tending towards the equilibrium point, it becomes stable. Now second is force system. Force means the driving source or input will be there. A system is stable See, concept is very important to understand. If you are not attentive in the class, then what will happen? Whenever the question like false and true, then fill in the blanks type question comes, then there the question comes whether you were truly listening in the class or your attention was elsewhere, like that. The concept, whenever you are understanding, it is very important to interpret afterwards. The system is stable if with bounded input. If it is with bounded input, restricted input, bounded input, the system output is also bounded, The two notions are very important. Means if it is a force system, then system is stable when with the bounded input and bounded output. The system becomes stable. Otherwise it is difficult. If it is bounded input and output is not bounded, it becomes unstable. Isn't it? So both should be BIBO. Bounded input, bounded output. Then the force system becomes stable. Now linear autonomous system, which we are talking about, with the non-zero eigenvalues. This linear autonomous system will be having system is having non-zero eigenvalues, isn't it? Now we are familiar with this non-zero eigenvalues. Then they will have their what you can qualitative behavior. They will show the qualitative behavior at equilibrium point. And if it is at the equilibrium point, then for entire state also, for entire state plane also, they will show its behavior same. So behavior of the linear autonomous system with non-zero eigenvalues, what is the qualitative behavior which is at the equilibrium point, same behavior it will show for an entire state plane. Okay, because it is stable. Now if it is non-linear, then what will happen? So it will have multiple equilibrium states. The system trajectories may be move away from the equilibrium point and tends to each other at the time progress. Means as x0 t, then x1 t1, the time changes, time progresses, the state changes, and trajectory can move away from the equilibrium point. So if there are multiple equilibrium points, that the trajectory or its behavior will not be qualitative. It won't be same at the equilibrium point and entire state plane. It will be different and it will move away from the equilibrium points. Or the trajectory can be, or it will not be bounded. It will move away from the equilibrium point. So it becomes unstable. So for restricted points, you can make it stable. But if you think about its equilibrium point and entire state plane, you can't decide its stability. It becomes unstable. Okay. Now we are not thinking about this. We are only linear autonomous system because our subject is linear system theory. So we are not talking about any non-linearity that will come in non-linear systems, non-linear control, isn't it? Suppose now we'll go ahead. Consider an autonomous system. Suppose consider equation B. What is that equation B? Who will tell me? This is the equation B. Assume that system has only one equilibrium point. Consider equation B. Consider autonomous system. Has only one equilibrium point. Consider it's only one equilibrium point. So the system of the equation B, so this system is stable at origin because origin can be one of the equilibrium point. So system is stable at the origin for every initial state xt0 which is close to equilibrium point, and ultimately the last stage, suppose last stage is xt, it also remains close to the equilibrium point. Are you understanding what is the meaning? So trajectory will be such that x0t will be near to the equilibrium point and xt also, which will be close to equilibrium point. So then it is stable. That's why it is stable. Now, second type of stability is restricted. There is conditional. What is that? It is asymptotically stable. So it is asymptotically stable. If xt, now your xt0 is close to the equilibrium point. Now what about xt for this asymptotically stable condition? So it is if xt in fact approaches to the origin, it will try to approach to the origin. But when it will come to the origin, that xt tends to infinity. So it is coming to 0, but when t tends to infinity. So in fact it approaches the origin at t tends to infinity. So there the asymptotically stability comes. So we can say that it is asymptotically stable in large. Why in large? Because of this infinity. Because of this infinity, we are adding this word. It is asymptotically stable in large. So if it is asymptotically stable for every, just a minute. Hello? Ah. What? Ah. Oh. अब मैडम माझं ऑनलाईन लेक्चर सुरू आहे मी थोड्या वेळात तुम्हाला if it is asymptotically stable for every initial state, means what? For every initial state it is asymptotically stable, means it is approaching towards 0 regardless how far or how near it is from the origin. Means if you are labeling the system as asymptotically stable, then for every initial state it is asymptotically stable. How far it is close to the origin or how far or how close, it doesn't matter. Once you are labeling this system is asymptotically stable, then okay, its every state is fine. We are fine with its every state, whether it is close to origin or far from the origin, regardless of for every step. Got it? So after that labeling, it doesn't matter then. For every initial state, it is close or far from origin. Means here it is not necessary that initial state must be close to the origin. It should chahiye, nahi chahiye. It is okay. It is asymptotically stable, so it is going to be 0 when t is equal to infinity. So initial state kahan pe hai? It doesn't matter. It is not required that it is close to the origin or not. But once it is labeled as asymptotically stable. So this is all, these are the words. Now mathematically how we can show it mathematically? Mathematically. So there we can, in terms of Euclidean norms, the system of equation B is stable at origin every real number, now it comes with the epsilon. If it is greater than 0, then there exists a real number delta epsilon greater than 0 such that, so these are the mathematically we have to put all the words concept mathematically. So for the system in equation B, which is autonomous, is stable at the origin for every real number epsilon greater than 0, there exists a real number delta epsilon which is greater than 0 such that norms x t0. What is it? This is the distance, you can say distance, isn't it? At which is less than delta results in, this will be the positive. Then also it is less than or equal to delta results in norm of xt which is less than delta epsilon for all t greater than or equal to t0. Means all t starting from initial to last stage. This definition is defined by this Lyapunov. It defines this method definition for stability. It is called as this definition by Lyapunov, definition of stability. It is a definition of stability. It's given by Mr. A.M. Lyapunov. Thus, he uses the concept of vector norm. Means he takes the help of vector norms and he put the concept of stability in mathematical form. This is the Euclidean form. This is the Euclidean form. Now, for vector x with n components, we know that this is all regard with the distance of a vector with n components. x1, x2, xn is the norm, that is a distance, which is given as x1 plus x1 square, x2 square, x3 square data dash and xn square. It is under root, isn't it? So we are familiar with this Euclidean norm. So that is x is less than r, which means r is going to the last limit, last radius, last distance. Everything will be inside that r. So x, that is the distance of x, all states which are less than r, which is less than r, is the hyper spherical region. S of r, it is called as of radius r, of radius r, surrounding equilibrium point. X is equal to 0. Means x is equal to 0 and surrounding the sphere is developed or it is made and which is of radius r. So every state which is inside that r now. And what you are saying, the distance of each state from the initial state, it is a positive. It is a positive and that means what? It is there and it is less than r. Means everything is inside r. So for any, now our epsilon is there, which is very small but positive number, which is less than r. Okay. So for any SE, epsilon, the designer must produce S delta, so that now our delta is less than epsilon. Epsilon is less than R. So S delta, so that system state initially in S delta will never go beyond S epsilon as shown in figure. Now what is the figure? You have to refer the book for this. The chapter number 13 is there for Nagraj Gopal for this, only this point. Okay. So it is, you can say this is the origin, then one circle and another circle. Okay. Then where the point will lie? If this is O, then this will be our delta and this will be epsilon. So this sphere will be S epsilon, this sphere will be S delta. And how the trajectory can move? Trajectory can move from, suppose it is like this. It will in between that sphere. So if it is x0, this will be xt0, this can be xt. It will be within that region. So उसको allow है, जितना घूमना है घूमो, जितना करना है करो. But it should be beyond that S epsilon. And S epsilon is under that SR. Okay. Now if this is A. Now if it is applicable to second order system also. It is example of second order also. So if you take a linear autonomous system whose space trajectory for various initial conditions, you can see in the second also. If we can show second order with R. Right. So what is added? Because of R, it is added. So this is O, this is R input. So this pair is S of R. This becomes delta. This is S delta. And this is what? Epsilon. This is pair of epsilon. Now how the trajectory can move? It can move because of the R. It can start from this xt and it can come back to here. So likewise it can move. So it is xt0. Because of R, the xt0 will be in the delta region from the R. Then it will be xt. It can move. So it is within the region. It is within the region. For the stability point of view, it is within the region. Okay. Mathematically, it is expressed. That's all. So trajectory whose maximum distance from the origin is R. For this trajectory, maximum original from the origin, it is maximum distance is R. And we select delta value less than epsilon. So S, this. It is chosen which will satisfy the coordinates of that guaranteed the stability. This is designer point of view. This delta is design. It is with us. So we have to select this delta such that the trajectory will be within the boundaries within this area of epsilon, S epsilon. So it will be, whatever may be the starting point, this trajectory will remain in the within S epsilon. So this is the design, and this is with us to give the guarantee of stability. So it is, next point is, a system is said to be locally stable. Locally stable. Stable in a small region, or stable, not stable in large, stable in small. It is locally stable. Stable in small. In stable in large means t goes to infinity. Means if the region S epsilon is small. Right? So if the region is small, it is a locally stable. So equation B, the system of equation B. What is equation B? It is a linear autonomous system. Equation of linear autonomous system. System of equation B is asymptotically stable at origin. Asymptotically stable at origin. Number A, if it is stable. B, there exists a real number. A real number R such that, which R is greater than 0, such that norm xt0 for all states less than R results in xt tends to 0 as t reaches to infinity. Okay. Then equation system may be asymptotically stable in large. This is about the small. This is about the small. Now, if the system of the equation B is asymptotically stable in large, then what that also will write. The system of equation B is asymptotically stable in large or globally asymptotically stable at origin when, if, number one, if it is stable, and B, for every initial state. If it is stable, then it can be asymptotically stable at a large. And for this, we don't know about its stability fix. Then every initial state xt0, if results in xt0 is equal to 0 at t tends to infinity, for every initial state xt0 results in xt0 tends to 0 in t is equal t reaches to infinity, means every state starting from initial state, it is not becoming 0 at the origin because it is not defined as stable. If it is stable, it is asymptotically stable. But we don't know about stability. But there is a chance that every initial state results in a zero. When the t reaches to infinity, we can say it is asymptotically stable in large. Okay, so it is user guarantee. So this becomes a asymptotically stable in large. So that every motion will approach to origin. Asymptotically stable means in large, that gives guarantee that कभी तो आएगा वो origin पे. That is it. कभी मतलब वो when t reaches to infinity, it comes back to origin. Means कभी तो आएगा means asymptotically stable in large. Okay, this is the concept. Stable है तो कोई problem ही नहीं है. If it is not stable, if it is stable, it will be asymptotically stable at the large. But if it is not stable, but it is going to be initial state are going to be zero at t tends to infinity, we can say it is asymptotically stable at the large. Limit cycle. Now, new concept is limit cycle. It is unwanted phenomena, limit cycle, but still from the limit cycle we can give the assurance whether it is going to be stable or not systems. So in the definitions of nonlinear system, the above system stability is defined in terms of disturbed steady state coming back to equilibrium. Are you understanding what I am saying? In the definitions of nonlinear systems, whatever we discussed, what is the meaning of system stability means system stability has been defined in terms of disturbed steady state. Steady state gets disturbed steady state coming back to equilibrium condition. So whatever the previous condition, steady state condition, whether it is coming back to its original condition, equilibrium position, after at least staying within a tolerable limits from it, we can say now, okay, it is coming back to stability. Coming back to stability. If it is not coming back to stability, it is not achieving its equilibrium point, it is not achieving its steady state, then it becomes unstable. Okay, means this system staying in the tolerable limits may exhibit a special behavior of a closed trajectory called as limit cycle. So I will explain again. The system system is there, it is in steady state. Now steady state get disturbed. Whether that steady state condition it is achieving after some time or not, that we have to check. If it gets disturbed once again, and if it is not coming back to its equilibrium condition, then it becomes unstable. But the system is staying within tolerable limits from the equilibrium point, and it is exhibiting special behavior of the closed trajectories called as limit cycle. So we can derive, we can found, we can sketch, we can get the behavior of the system with types of limit cycles. Limit cycle is unwanted. But what happens within tolerable limit, if special type of behavior it is showing, which is tolerable, within tolerable limits, it is around the equilibrium position, we can call as that trajectories, these are called as limit cycle. So the limit cycle describes the oscillations. Limit cycle describes the oscillations of nonlinear system. The existence of limit cycle corresponds to oscillations of fixed amplitude and period. Okay, so where you observe this behavior, oscillations with the constant amplitude and period, on the S-plane where the poles are located, you have this oscillation which are not damped oscillation, undamped oscillations are there. Where you find? You're sitting idle or sleeping? you sleeping?
No, ma'am, no sleeping. Listening.
Okay. Then where you find on the S-plane undamped oscillations on the imaginary axis, right? When the poles are on the imaginary axis, you got this undamped oscillations. Means there they exhibit the limit cycles. So limit cycle for the within tolerable limits and intolerable limits, I will draw it so you will understand. Stable limit cycles. This is x1 point, x2 points are all these points. So this is going to be so here, suppose it is started, then these are the limit cycle. These are trajectory can be, but these are the bounded within tolerable limits there. So only one way there is there. It is going inside and having the limit cycle and it is approaching. It is not approaching towards zero, but it is there. It is there, and within the boundary, within the tolerable limits, there the trajectories are formed. Since path is in the neighborhood, so what are the path they are taken trajectory? This path is in neighborhood. Is in neighborhood. Converges the limit cycle. Limit cycle that converts because the path is within the neighborhood. But for this second type of trajectory, here, how they are there? It's multi, you can say. You can say this is the way. So we can decide its path. It is going away from it. So these are the unstable limit cycles. The path in the neighborhood of limit cycle or closed trajectory diverge away from it. The path in the neighborhood of limit cycle. That limit cycle is a closed trajectory. Limit cycle is closed trajectory, but it is not within the tolerance, which is it is going to diverge away from it. So it is going away. Here also going away indicates the limit cycle is unstable. Indicates limit cycle is unstable. So observe this first and second. So it is path is within neighborhood of the limit cycle. So it is converged. Now it gets diverged. Okay. So it is unstable. It is stable. Okay. So this is the concept. Now main direct method of Lyapunov stability analysis is remaining. Should I continue or what you can say? Because I was expecting I can finish this full concept within this lecture. Half an hour is required. I think I require half an hour to explain the Lyapunov stability criteria Then I have to explain the direct method for the direct method of Lyapunov for the linear system. These 2 points are still remaining. This was the only background. This was the only background or concept to understand the Lyapunov stability for the actual stability for the system and then direct method for the linear system. Yes, should I continue or stop? If I'm going to stop, then when I can continue or when I can start, that also you have to tell me. Because here I'm sitting, I'm here in the college. Yes, please tell me whether I should continue or because here first part is over, second part is remaining. There are two parts for the Lyapunov stability criteria. The first part is over where we get the what is a prerequisite for the second part. That is over. You're writing something in chat box? I don't know. I have to check. 15 students are there. Yes. I won't mind if you say, madam, please stop and you can continue after some time or tomorrow or whatever. Or if you want, you can send me, continue, madam. Hmm? Yeah? Continue, ma'am. Continue?
Okay,
Okay.
continue, madam.
Okay. Don't sleep, huh?
No, yes.
Because I can't see your faces now, whether you're sleepy or not. In the class, it is easy to tell you go and make yourself fresh and come back, isn't it? Okay, I'll continue. So till now we have learned what is stability, stable, stability, stable, and asymptotically stable. What is limit cycle, and how to identify for the asymptotically stable in the large and in the small. Okay, now we'll quickly move towards the actual Lyapunov criteria and the Lyapunov stability criteria for the linear system. Okay. Now write in your notebook. Second part, that is B part, is Lyapunov stability criteria. Stability criteria. I cannot write. My handwriting is not good with the stylus. Please tolerate. The general state equation for nonlinear system is x dot is equal to f of xt ut for all t. Okay, this is the nonlinear system general state equation. General state equation for nonlinear system. We'll understand stability criteria for non-linear and then we apply for the linear direct method. Because this is the basic or prerequisite to understand the stability criteria or which is direct method for the linear system. This is the basic or prerequisite. That's why we have to learn this. Non-linear system. Okay. So analytical solution of this is rarely possible because it is non-linear, isn't it? Non-linear system analytical solution is rarely possible. It is not possible to find out. So what we'll do, we'll apply basic stability theorems and we will find whether it is coming in that area or not, area of stability. Okay, we are bringing that nonlinear system in that area and we are finding whether it is stable or not. So basic stability theorems, which is invented or it is shown by the Liobanov. Basic stability theorems. Okay, so direct method of Liobanov is based on the concept of energy. This method is based on concept of energy. Have you studied it before? If it is studied, I'll omit that part. If it is not, then I'll explain. It will take few minutes. The direct method of Liobanov is based on the concept of energy. Energy is a positive number, right? And its relation of stored energy with the system stability. And the relation of energy with system stability. Now how it is decided? So if we take an autonomous physical system, autonomous physical system, it is autonomous, but physical system means with T it will be there. So x dot T is equal to f of xt, because T comes, which is a physical autonomous system. Let x of xt0 T be the solution. Solution means this satisfies the equation. Solution. And further, V of x will be the total energy. V of x will be the total energy associated with the system. With system. Okay. Then the derivative, if the derivative of dVx by dt, this energy, derivative of this energy is negative for all x0 t except the equilibrium point. Why? Because equilibrium point is 0, 0. Except the equilibrium point. Except the equilibrium point means dV by, this is energy, derivative of energy is negative for all states, x1, x2, x3, x4, x1, x all states except the equilibrium points. Then what is that? Then it follows that I'm writing his statement, so it is in his statement only. It follows that energy of the system decreases. I don't understand. Negative means it is decay. Decreases as T increases. As T increases. As T increases. And finally, it comes to rest. Or it becomes zero. Isn't it? Finally, the system will reach the equilibrium point. Rest means it will come to the equilibrium point. Equilibrium point. Okay. This holds because energy is non-negative function. Energy, I told you, energy is a positive. It is a non-negative function of the system state, which reaches to minimum only if the system motion stop. When the system motion stop, energy is zero. Kinetic energy or potential energy, it becomes zero. Okay, at the stop. So this happens where? At the equilibrium. So this idea, you know that if there is a mass and damper example is given and it is explained with the mass damper system. So how it is there? It is, you know that this is the system which is moving here, and this is the mass spring with the K as a constant, and this is what, and what is the equation? X1 double dot plus F x1 dot plus kx1 is equal to 0, which is the mass damper system governed by this equation. This is the equation. State model of this equation is what? State model is x1 double dot is equal to x2. Sorry. X1 dot is equal to x2 and x2 dot is equal to, from this equation we can find out x2 dot is minus k x1 minus f x2 from this. At any instant total energy V in the system, at any instant total energy is when it is this is a mass damper, so it is having potential energy at the same time kinetic energy also, isn't it? So total energy V in the system consists of Ke and P because of spring and kinetic energy because of the moving mass. This is because of moving mass. Okay. Then what is said, or what is the statement of this energy associated with x1 and x2 of the states is equal to, which is energy, what is 1/2 x2 square plus 1/2 k x1 square, isn't it? Spring और ये mass का दोनों का energy we can add it, that will be the total energy of x1 and x2. So what is said here? V of x is greater than 0 because it is what? It is non-negative term. It is a energy when x is not equal to 0. Thus V of 0 will be 0, isn't it? This means total energy is positive unless the system is at a rest. Got it? Total energy will be positive unless the system is at rest, at equilibrium condition. So what was our point? Xc is equal to 0, where energy will be 0. Energy will be 0. Right? Now we are dealing with the derivative, rate of change of energy. So the because of Lyapunov, because of not me, it is because of Lyapunov. The rate of change of energy this equation you Remember, x1 is equal to x2 and x2 dot is equal to minus kx1 minus fx2. Rate of change of energy is given by d by dt of v of x1 and x2. Got it? x1 and x2. So how? Dabba v by dabba x1 dx1 by dt plus dabba v by dabba x2 dx2 by dt. So if you do it, all of you do it. So what is it? Dabba v by dabba x1 of this x1. So x1 क्या है? This is x2. dx1 by dt is x. What is it? This x2. So put up over here x2. So what is dv by dx1? This. From this equation you find out. So what is it? Huh? Dabba v by dabba x1 is to get cancelled. It is kx1, isn't it? kx1. Here. 2 gets cancelled and it gives you kx1. दूसरे का क्या होगा? What is dx by dt? ये whole equation x2 dot. So minus k x1 minus fx2 minus kx1 minus fx2. Okay. So what is dabba v by dabba x2? क्या हो जाएगा? x2. Now solve this. So ये इसके साथ जाएगा बंदा. What is remaining? Minus x2 into x2 because it is going to multiply over here. Minus f x2 square. So thus dv by dt is negative. Got it? It gives negative sign. Thus dv by dt is negative for all points. At all points where x2 is 0, except I forgot, except is 0 at which dv by dt is 0. Thus dv by dt is negative for all points except where x2 is 0 at which dv by dt is 0. Therefore, under positive damping, system energy cannot increase, isn't it? What is this equation? x1 dot is equal to x2. It is saying, we observe that x2 dot is equal to minus kx1. So at the points where x2 is equal to 0, the system is cannot remain in non-equilibrium state for which x2 is equal to 0. ये बंदा x2 dot is what? Minus kx1. So इसका differentiation होगा. Though it is x2 is 0, we will have its value. We will have its derivative, isn't it? Thus the system cannot remain in non-equilibrium state for which x2 is equal to 0. So x2 is equal to 0 है. But what we are getting? Its value we get negative. Derivative value. On what is our Liopenau says? Say it is an derivative is negative. If it is negative, it becomes in an equilibrium state. So it will not remain in non-equilibrium state, means it remains in equilibrium state. Therefore, energy cannot remain constant except the equilibrium point where it will be 0. Okay. So it is going to change. The visual analogy of the surface is, suppose V is equal to what? 1/2 x2 square. These are the energies. K x1 square. So for this points, how it is derived. This is x2 and this is x1, and for this how energy is shown. So energy will be more. Energy will be more as the states are more. You're going away from the equilibrium point. So equilibrium point is here. Equilibrium point is here. So this will be first V, second V, third V, V3. This will be V, and V3 will be more than V2 and V1. And at this point, it will become 0. It will become 0. So for the trajectory point of view, how we can show? This is x1, this is x2, this is x2, and how it is moving for V1. Say, suppose this is the point, it comes. For V1, it is moving. For V2, it is from this. For V3, it is from this. Okay. So it is any certain part x10, x2, x20. This is the point where it is crossing, and these are the V1 state for V2, and this is V3. This is x1, this is x2. Okay, so this is the cup-shaped surface is there, but the constant loci are the eclipses on the surface, you can say. And what is this point? Let x10 and x20 the initial condition. And if you plot the trajectories on the surface shown, where the point xt crosses the constant v curves, this xt, which is the initial point, and now this crosses this. This becomes xt. So particularly this will become x3, x3t, x2t, x1t, right? This crosses the constant v curves and move towards the lowest point of cup. Or when it is reaching over here, this will be here 0, and this will be the reaching towards point. So this is the typical trajectory on x2 and x1 plane. Okay. So this we understand the concept of Lyapunov's concept of energy. Using energy concept, he defines the stability. He defines the stability. If it is happening, means if the energy is 0 at the equilibrium point and it goes on decreasing, as it go towards the equilibrium point, if the energy goes on decreasing, means it is becoming stable. The system becoming stable. That is okay. But actually, what happens if we cannot put up the system in the Lyapunov form, in this energy form? Then what should be done? That is one of the limitations. Another is that what means if there is not possible to show in terms of energies and energy point of view, it's very difficult. Then again that prediction comes, isn't it? But irrespective of this limitation, we use this Lyapunov stability criteria for the linear system also, and that is known as direct method for the stability in the linear systems, in the linear systems. Okay, but for this, what is here? For the condition, if it is not proving that, then also we have one condition is that I told you, asymptotically stable in large, asymptotically stable in small. So that point is there. If all conditions are there, so what are the conditions? Number A, V of x. Okay, V means that energy is greater than 0 for x, which is not 0 for all points. If it is greater than 0, okay, we can say it is going towards stability. If V0 is equal to 0, okay, second condition. Yes. Then third is what? V of x has a continuous partial derivative with respect to all components. Has continuous partial derivatives, double v, that is partial derivatives with all with respect to partial derivatives with respect to all components. All components are all states of x. Okay, if this is possible, then go ahead. If v of x is greater than 0 for all except the origin, if v of 0 will be 0 at origin, if v of x has a continuous partial derivatives with respect to all components, if it is there, and the dv by dt is less than or equal to 0, because dv by dt is dv by dt is negative semi-definite scalar function. It is, that's why it is written is equal to 0 also. It can come 0, but it is a negative. Then system is done. System, see what I am writing is important. System is stable at origin. At origin. And if dv by dt is less than 0 for all x except x is equal to 0, dv by dt is negative definite scalar function, then also the system, if the property d means this abcd wala d, if the property d of the theorem 1 is replaced with the, this is theorem 1, this is theorem 1, there is all property 1 2 3 4. Okay, now this theorem 2, what it is saying, if the property d of the theorem 1 is replaced with, if d of 1 is replaced with another d, what is d? dv by dt is less than 0, is not equal to 0, less than 0 for x greater than or equal to 0, that is dv by dt is negative definite, here semi definite word is there, and here the negative definite. So what is the definite matrix and all that we will see, that is given in the appendix also, but we will see that what is it, negative definite scalar function, and it will be negative definite. If it is semi-definite, it will be less than or equal to 0. If it is negative definite scalar function, it will be less than 0. And if it comes, then we accept what x will be eventually approached to 0, then x will be eventually approached to 0, and we can avoid the rigorous proofs for A, B, C. We are not going to check. If x is approaching 0 and when t reaches to infinity and this dv by dt is less than 0, then we can say that v of x is infinity, as for the all norms x is infinity, means system is asymptotically तो x बढ़ जाएगा infinity तक, तो v of x भी बढ़ जाएगा infinity, isn't it? So system is asymptotically stable So we are not talking about now T. We are talking about the energy. We are talking about energy. Energy will be infinity when the x will going to be infinity. X बढ़ जाएगा infinity. The system is asymptotically stable in large. In the large. Got it? So what is here? If it is system, it is replaced. If you got dv by dt is less than zero, ये बाकी का छोड़ दो. फिर if you can find v of x is infinity for x is all x is approaching towards infinity, this energy will become infinity. ये है, then it's okay. System is asymptotically stable in large. That's all. टप्पा लगा दो, हो गया काम. Okay. This is the way you have to understand the system and understand its stability. Okay. Now, the next one, proof is there. And after that, we will solve the example. What is a proof? It's a direct method of Liobanov for the linear system. So here, now we are reaching towards our actual thing, that is the direct method. I'll write here. So you also just note down in your notebook, direct method of Liobanov and linear system. Linear system. Okay, now we will start. Consider a linear. This is important from your syllabus. Consider a linear autonomous system. Linear autonomous system described by state equation. X dot, you're familiar with this. X dot is equal to Ax. Number one. The linear system is asymptotically stable in large at origin. The linear system. Well, think about the worst only. Okay. We are not thinking about the stable. It is linear system is asymptotically stable in large, we have to write in the large at origin, if and only if this statement, if and only if given any, now we come in our area. What is our area? Matrix. So given any symmetric, if given any symmetric positive definite matrix, definite matrix Q, there exist. What happens in a Q matrix such that all the row and column atoms are there, no? Numbers are there. If you find a minor of each, it should be, the determinant should be greater than 0. It must be positive. Then it called as positive. It should be symmetric and positive definite. Means all the values of minor will be greater than, determinant value will be greater than 0. Okay. Positive definite matrix Q, there exists if given any symmetric positive definite matrix Q, there exists a symmetric positive definite matrix. इस ये Q तुम्हारे पास है तो दूसरा आ जाएगा. दूसरा क्या है? There exists a symmetric positive definite matrix P, which is nothing but it's a unique solution. So ये बंदा आपके पास है Q, तो ये आ जाएगा P. P is what? The solution of this your autonomous system. Q solution, which is the unique solution. Unique solution. So what is the relation? It's A transpose P plus P A gives the minus Q. So when this relation is happen, it is true, then the linear system is asymptotically stable in large. Okay, so the linear system is asymptotically stable in large at the origin if and only if given any symmetric positive definite matrix Q, there exists a symmetric positive definite matrix P, that is unique solution, such that A transpose P plus P into A is equal to minus Q. So what is it? Is a few lines of proof we will see. What is a proof? To prove the sufficiency, we will find out this. What is it? V of x. Now we are aware with this. V of x is a x transpose px. Scalar function, that is, what is it? Let us assume that symmetric positive definite matrix P. I'll write that. Instead of talking, I'll write. Let us assume a symmetric positive definite matrix P exist, which is a unique solution for this equation. This is number 2. With which is unique solution of equation 2. Consider a scalar function. This is the scalar function will be. We have to. Why this is there, I will explain it. But right now you consider it. V of x for matrix in the, it is not in points form x1 and x2 जैसे लिया था last time. It is not. It is a matrix. For matrix, this will be the state transpose xt. P is a solution and this will be x. Okay. So Vx of Vx will be x transpose P into x. That will be V of x. Why this scalar function is considered scalar function? This is the scalar. This is what? Scalar function. In terms of this V. V is a what? Energy. Energy. Note that this given in appendix, so I will explain that why. But let me finish this proof. V of x is greater than 0. V of x is greater than 0 for x not equal to 0. Okay, we know that. Now v of x is greater than 0. And we also know that v of 0 is 0. Okay, the time derivative of v of x of v of x is v dot x. V of x is v dot x. So what is v dot x? V dot x is equal to x dot ट्रांसपोज, इसका x डॉट हो गया p of x प्लस x ट्रांसपोज एज इट इज p प्लस x डॉट, इसका डेरिवेटिव फिर इसका डेरिवेटिव यूजिंग इक्वेशन 1 and 2. One and two. What is one and what is two? This is 2 and this is 1. This is 2 and this is 1. So what we are going to do? We are writing the value v of x. So just check. V dot x is equal to x transpose A transpose px plus xt transpose pax. What is done? x dot क्या किया? इसका वैल्यू कर दिया. x dot value is substituted. Then what is x transposes? X transpose p plus p a x.
लेक्चर चालू आहे. बरोबर, करेक्ट करेक्ट.
So what ultimately
CVP मध्ये
when you solve it,
CVP ला लागली.
what is it? A transpose p plus pa is minus
चालू
q.
आहे ते पण.
So इसका वैल्यू है minus q. Substitute करो. So minus x transpose
हां,
qx.
तिकडेच चालू आहे.
बरं.
See here.
तर
This is what?
कनेक्टेड
This
राहा.
is such.
कसं चालू आहे? पेपर होता का?
हा पेपर आहे आता बस चालू.
कसा गेला?
Since q is positive definite, now what is our assumption?
प्रोडक्शन प्लॅनिंग
Since
कंट्रोल.
q is
अच्छा.
positive
काय
definite,
म्हणजे एंड सेम आहे का?
एंड सेम
एंड सेम. अच्छा. करा चांगलं.
हो.
हां.
right?
भेटू.
What is your result? V dot x is negative definite. Yes, v dot x is negative definite. It's a scalar value, no? So norm of x may be defined. So norm of x. So for all x, what is the norm of x? For x is equal to x transpose px. That is we find the distance. That is x transpose px under root. Okay. So because only one we have considered only one, that is under root. So v of x is equal to x square. Means what? V of x reaches to infinity as all x reaches to infinity. V of x reaches to infinity. All x reaches to infinity. So x is defined like this. Okay. Now system is asymptotically, and that's why system is asymptotically stable in large at origin. from the theorem 3. But for all this condition, but for this condition, the positive definiteness of P is necessary, is very important. P must be positive definite, necessary and sufficient condition. Okay, so I will underline this. Sufficient for asymptotically stability of the system. So I will understand this. I will, underline, or I'll make it positive definiteness of P is required. So when you find out that P matrix, that is solution of the system, and if it is positive definite, then you can say that a system is asymptotically stable. If you get a matrix of P, when you solve example, and if you get a matrix P such that there is no positive definite, it is a negative value, it is coming, when you solve it, when you determinant you calculate, and then you can say it is not asymptotically stable in large. Okay, so we'll solve an example which is also given in the book. In exam, what happens? Only the figures are changed. That is, the method is changed. The question pattern statement is not going to change, because you people should not get confused. Then also you got confused in in mid-sem. I don't understand why. But now you change it. You understand everything and you interpret it, or you write it accordingly. Let us determine the stability of the system described by following equation. Now what is given example is